this video is covering vectors and their use in calculus. Now, it's a pretty brief introduction to vectors and they're not very much used in calculus, but they're pretty easy to catch on. If you're in physics, you've used vectors a lot. So this is just kind of an introduction and how you'll see them in calculus. So if you're in physics, I still really need you to watch the video just to see how they're used in this course. Okay, so just kind of an introduction with vectors. A vector is called a directed line segment. So a vector both has a magnitude, a size, and a direction. Now there's two ways that we can represent a vector. I tend to like one more than the other, but I want you to be able to see both. So when we notate vectors, this little V, it has an arrow on the top of it like that, so that's how you would know that we're talking about a vector. And then how we write them, we can write them one of two ways. We can write it this form, which is actually my favorite, with the chevrons, the angle brackets, which is called component form. Or we could write it, we have the IJ format, where I is like the X component and J is like the Y component. Like I said, I typically won't use the IJ. I'll typically use the component form with the chevrons. Okay, so it's actually why I'm doing this as the same time as the parametric is it's actually very similar to parametric in that we have the X component and the Y component. All right, so the magnitude of a vector is denoted by, that's incorrect in your notes. The magnitude of a vector is actually 2 bars instead of 1 bar on either side, so that's how we notate the magnitude. If you were to do, I'm going to go ahead and skip to number 1 really quick. If you have the vector 2, 3, typically our standard vectors are going to start with their initial point in the origin. So if you're not familiar with vectors, this is how it would look. So if I'm starting at the origin and then I have an X component of 2, that means it's moved 2 to the right, and then a Y component of 3, that means it would go 3 units up. So if we start at the origin and our vector, it's not the point 2, 3, it's this line segment kind of that goes from the origin to the point 2, 3, and they have an arrow on them to show the direction. Okay, so this vector, what it has when I talk about magnitude and direction, the magnitude is talking about the length of that arrow. Sorry, I should have done this in a different color. Okay, so that length of that arrow is the magnitude. Okay, and we can calculate that distance because if you look, we have this right triangle, and so that would just be distance formula or Pythagorean theorem, which is this right here. So the square root of, this is my X component, right, of 2, this is my Y component of 3, and so then you would use Pythagorean theorem to find the magnitude. Okay, then we also have a direction. So this kind of like the slope, right, of 3 over 2 is kind of putting me in a certain direction. So I could have the same magnitude, but in a different direction. So the direction is actually related to polar graphs, which we will study later, but we can still look at the vectors here. The theta, just like in polar, we start at the positive x-axis and go this direction right here. That's the theta. Okay, so that tells you in what direction is this vector going. Okay, so that's what I mean by both magnitude and direction. All right, so to find the magnitude of the vector, we already talked about is the Pythagorean theorem. And then to find the direction, to find that theta, notice that in our triangle, theta, we have the opposite of 3 over adjacent of 2, and that's tangent. Okay, so tangent of theta equals y over x, or theta just equals the inverse of tangent of y over x. Okay, so given our vector of 2, 3, we want to find the magnitude of the vector, which again is just going to be the Pythagorean theorem. So that would just be the square root of 2 squared plus 3 squared, which would be the square root of 4 plus 9, which is 13. Okay, so that vector has a length of a square root of 13. To find the direction of our vector, we say that theta is equal to the inverse tangent of our y component of 3 over our x component of 2. And if you were to put that in the calculator, make sure you're in radian mode, that would give you approximately 0.983. Okay. And now for part C, it says to write the vector in polar form. We're going to wait. We're going to come back to that part after we've learned polars. The rest of it is fine. We can do the rest of this lesson without polars. All right, so an important thing, and this is why we use this in physics, is that velocity is a vector. Because velocity, when we talk about velocity, it both has a magnitude and a direction. If I'm traveling at 30 miles per hour, and that's my velocity, that's my speed, right? Because that's my magnitude, that's how fast I'm going. But in which direction am I going? So, you know, I could be moving forward or I could be moving backward, and that shows the direction of where I'm going. So like I just said, speed of a velocity vector is the magnitude, right? So this is really important. Again, if you're in physics, this is easy for you, but that's something that you need to memorize. All right, so since we've learned about parametric equations, I said that parametric and vectors are very closely related. So consider the parametric equations of the x component and y component. So if you have a function of that form where you have that, let's call it a new function, we're going to use r, is equal to that x component times I, and these should have like little arrows on them, sorry. And then the y component of g times the j vector is called a vector valued function, and you're going to see that wording more often. So it's basically if you take parametrics and then put them together, you have a vector valued function. Now the ij format might be confusing for some of you, so I just do this format. So if you just write it as a vector, so when you write something as a vector, you either use the ij's or you use the chevrons. So if you just say the vector r is equal to, in chevrons, our x component function, comma, our y component function, that's a vector valued function. Okay, so like I said, they're very, very closely related. All right, so you can use vector valued functions to represent motion along a curve, just like parametrics. The terminal point of the position vector, which we call r, corresponds with the point xy on the curve of the parametric equation. Okay, so let's kind of see how this correlates. So given x, the x component being t squared and the y component being t cubed, that's a parametric equation, write this as a vector valued function. So to write this as a vector valued function, we're going to represent this with r, and we have to put the vector on top of that r to show that this is a vector valued function. And this is going to equal, I'm going to use the component form with the chevrons. So it's just my x component, comma, my y component. And that's it. That's very, very easy. It's just knowing how something looks as vector valued. Now it says to find r of 1, r of 2. So that means my position vector at 1. And so that all you have to do is just plug in 1. So 1 squared is 1, 1 cubed is 1. Very easy. All right, and then also our vector evaluated at 2, just plug in 2 for t. So we have 4 and 8 is my vector for that. Okay? All right, so that's just kind of a brief, very, very brief introduction to vectors. And so now we're going to talk about calculus with vectors and finding the derivatives, but it's couldn't be easier. So if we have a vector valued function and we want to take the derivative of a vector valued function, all we have to do is take the derivative of the x component and the derivative of the y component, and you're done. So using the example information from example 2, if this r is our vector valued function, then find r prime. It's quite easy. So the vector r prime of t is just simply equal to the derivative of the x component, which would be 2t, sorry, and then the derivative of the y component, which would be 3t squared. Quite easy. All right, and so now, of course, the second derivative would be just the second derivative of both components, which would be 2 and 6t. Okay, pretty easy. All right, so now if we relate this to position, velocity, and acceleration, we would call the position vector that original r, so then r prime would represent the object's velocity. So that would be the velocity vector, and the second derivative would represent the object's acceleration. So both velocity and acceleration are vector quantities because they have both magnitude and a direction. All right, so last question. So the direction of r prime, again, that's a vector, gives the direction of motion of the object at the time t. The magnitude gives the speed. I know I already said this, but this is super, super important. So when we talk about speed, speed is not a vector, so it will not be written in that component form. Speed is just a scalar. That means it's just a number, it's just a constant. So when I ask for speed, do not give me a vector. So speed, we start with the vector for velocity. So that is, we would have from previous, we had, what was it, 2t and then 3t squared. Okay, so that's the velocity vector, but if I asked you for the speed, then you would calculate the magnitude of that vector, which I already said is basically the Pythagorean theorem. So it would be the square root of my x component squared, which we're talking here about derivatives, so that would be x prime of t squared plus the y component squared. Okay, and that would give you the speed. You need to memorize that. Okay, all right, so this is just continuing on. Definition of velocity and acceleration. We've already talked about this. If you have a vector value function, now I know this is using ij's, but you can also use the chevrons. So if you have a position vector, which is your x and your y component, then your velocity is the derivative of those, acceleration is the second derivative, and the speed is that formula that I wrote up at the top. Okay, so now let's do a couple of questions using this. So find the velocity vector, the speed, and the acceleration vector of a particle that moves along that vector value function. So again, this is using ij's, but you can easily convert that to the component form by just saying that's 2 sine of t over 2 and 2 cosine of t over 2. Okay. Again, typically you'll see, I don't think I've ever seen the ij form actually on the AP test. I've almost always seen it as a component form. So now, that's the position vector. So to find the velocity vector, we take r prime, which you could call that v of t if you wanted to for velocity, and just simply take the derivative. So the derivative of 2 sine of t over 2 would be 2 times cosine of t over 2, and then times that 1/2 because of the chain rule. So that will cancel out with the 2 in the top, so this would be cosine of t over 2. Similarly, the y component would be negative sine of t over 2. Okay, now I'm going to stop there, and we're going to find the speed, and then we'll go back and find the acceleration vector. So the speed, you have to have the velocity vector first, is going to be the square root of that x component of the velocity squared, which actually I'm going to rewrite that as cosine squared. So cosine squared of t over 2 plus negative sine t over 2 is going to be positive when you square it. And then you have cosine squared plus sine squared of the same argument, which is just 1. So for this function, the speed is a constant of 1. It's just going to be changing direction. All right, and then finally for the acceleration vector, that would just simply be the second derivative of our position vector, which here would be 1/2, negative 1/2 sine of t over 2, and negative 1/2 cosine of t over 2. And that's it. Okay, very, very simple. All right, so very last question. So number 5, an object starts from rest. That's extremely important. We start from rest at the point to 0. So starting from rest is telling me about the velocity, the initial velocity, and then starting at this point, that's my initial position. And it moves with an acceleration, and they give us a vector of 1i plus 2j. So that means if you want to write that as a vector in component form, that would be the x component is 1 and the y component is 2. Okay, where this is not, and then the absolute value of, or actually really it's the magnitude of the acceleration is measured in feet per second per second. Final location of the object after t equals 2 seconds. Okay, we've done this before, just not as a vector form. So if I want to find position given acceleration, I take integrals. So the integral of the acceleration vector would be the velocity vector. And so again, you just simply take the integral of 1 with respect to t, so that's t. And actually, remember when you take an integral, you do have that plus c value, and I'm going to call that c in the x direction. And then you would have 2t plus the c in the y direction, because the x component and the y component. Now, that c is the initial value. And we already said that the object starts from rest. So you know that since your initial velocity starts from rest, that those would actually just both be 0. Okay, but that's important to know that because it might not have started at rest. Okay, so that's just t and 2t. So now to find the position vector, we want to take the integral again. And so this would be r. And so the integral of t would be 1/2 t squared, remember, plus c in the x direction, and then t squared plus c in the y direction. Now, again, those are our initial values, and so that comes from the point up here. So my starting point had a starting c value of 2 and a starting y value of 0. So my actual position vector would be 1/2 t squared plus 2, and then t squared. So now if you want to calculate, find the location of the object after 2 seconds, then you would just calculate your vector after 2 seconds, and that would be actually 4, 4. So the position, we don't write that as a vector, is 4, 4. Okay? All right, so that's just a brief introduction to vectors, but if you know parametric equations, they're very similar, just kind of written in a different way.